The topic of this lecture is on evaluating programming languages. The important thing for this topic is to understand that when you're evaluating a programming language, you want to take into consideration what you're using that programming language for. So this lecture covers some of the ideas that researchers have found, some reasons why we would even want to evaluate programming languages, and then just going through some examples. Before diving into the rest of the lecture, I thought I'd start with a summary of the programming paradigms that we've covered so far. There's a lot of different paradigms, but the ones that we've been focusing on in this class was four main paradigms. Imperative, which is the early style of programming, and that is typically a sequence of commands. It's very step-by-step. We also briefly touched upon functional, logic, and object-oriented programming of the paradigms. You learned object-oriented programming in 1115 and 3130. 1115, 3115, and 3130 because those classes focus on Java. Java is definitely an object-oriented programming language. Functional and logical are a little different. You may or may not have seen it before, so that one's maybe like a little hard to picture in your mind right now, but the point of bringing this up is to remind you that there's different programming languages and the motivations for why they were created can connect to roughly like the characteristics of how we might describe them when we categorize them into paradigms. So learning objectives for this lecture, we want to just kind of go over why we would even care to think about the programming language design. The main point is that the way the language is designed, the features of it, the expressions that you can create will affect how you can think about the problem that you're working on. So choosing a language is really about finding the right tool for the job. There's some attributes that some research papers talk about for describing what is a good programming language. So we'll cover that a little bit. And then how would you evaluate? Well, typically you'd come up with evaluation criteria. There's another paper that talks about some reasonably good evaluation criteria that you can use. And finally, we'll end with some of the best practices when using languages. So the first thing, language affects how we think about problems. There's actually someone who wrote a book about this phenomenon. He is a linguist. And when I was reading about him, like his biography, I found out that he is a fireman by day and linguist by night. His name is Benjamin Worf. He studied at MIT. He studied languages, human languages. He studied how people express themselves using human languages. So his quote in the black box here, language shapes the way we think and determines what we can think about. Just offhand, slightly different. Perhaps you have heard of how like people from different cultures may have a lot of like similar concepts, but then depending on the language, how people build a sentence in their language, they may think and view the world in a different way. So that's kind of what he's talking about here, that our reality, like our ability to express ourselves, can influence our thoughts can influence our language, and so on. What I'm trying to do is borrow this idea of the human languages impacting your ability to express yourself from human to human is going to be in parallel to when you're working with a programming language. You will also feel impacted by how you can express yourself in a programming language. Some more quotes from him. And then just a funny meme on the side there that just kind of gives a sense of like each programming language has its quirks. You might see more memes out there, and I think I have a few more towards the end of the slide deck. Just each language has its own characteristics. So for instance, Java is very verbose, and so on. Unix shell, I don't have permission to read this. If you've used terminal before, you might understand what that joke's about. So what I wanted to focus on with the diversity of languages is some languages require the programmer to be very verbose, like Java. Then other languages may require configuring things in a certain way, or just defining all the data objects, before you can begin writing the logic. So just a little bit, tying back to the early part of the semester, we were talking about there is an evolution of programming and how over the years different paradigms came about because people realized you have to be able to maintain code in a certain way, or maybe you need some sort of feature that allows you to write the code in the first place. Anyway, so just kind of like going back to those different eras of programming. So the early days, and I'm talking about with software level of programming, the early days was like 1950s, 1960s. This was after World War II. So it was definitely after Alan Turing and his machine that was used in solving cryptography puzzles. In the 1950s and 60s, it was the age of algorithms. Like, there was a limited amount of hardware, and there was a strong emphasis back then on getting your thought out on paper, working through the problem, testing out your idea prior to implementing your code. So that's where the idea of separating what you're working on into two different parts, like pseudocode, planning, analysis, all of that before implementing in code. And so back then also you had people who specialized in the two different parts. So some people focused on the system analysis and design, others focused more on being the code monkeys who turned the design into actual working code. Furthermore, those who were the code monkeys had a more direct connection to the hardware. They really had to keep track in their minds as they're working on things, working on the code. They had to think about the memory and keep track of a lot of stuff in their head. And because it was so difficult to program back then, inventions came about, more abstractions came about, more language features came about. So today, in today's world, we have a lot. For instance, when you're learning about Java in 11.15 and 31.15, you go through all the different interfaces and classes available with the language. You go through all the different conditionals and looping features, and then how to write classes and inherit from different classes, and so on. So back then, definitely it was imperative in like the 1950s and 60s. They were definitely working on imperative code. Their main novel idea with maintaining code was structured programming, which allowed for procedural abstraction, so they could reuse code blocks, and that really saved a lot of time, over repeating the same exact code in multiple places. So I just want to end with the note of times have changed since, 70 years ago until now. So in the 1960s, that was the time when NASA was trying to send the first man to the moon, or rather it was a team of people, but the U.S. was competing with Russia, with their Cold War. I'm not going to cover too much about the history because you'll probably learn about it in history class, but what I wanted to say was this picture here is Margaret Hamilton in the late 60s. She was working at NASA on the Apollo space shuttle, and they had a lot of code in, a lot of software. So a lot of coding was required for this project. And I just pulled some quotes from this link below that I thought were relevant and interesting. The pile of books that she's standing right next to is the printed version of all the code. So there was a lot of code. That was definitely a project that inspired more ways to, I guess, manage code. I don't know exactly what was invented, but a really big project such as that required being able to test rigorously, to be able to maintain a working knowledge of all the various different variables that are defined, and then all the logic that the whole program would need. The system that they worked on back then had very limited user interface features. So in today's world, in our computer screen, when we enter an operating system, when we enter a website, we definitely have a lot more happening in terms of a nice user interface, a GUI. It is more of a graphically rendered UI, whereas back then on the Apollo system, they had these LED screens that are like what you might see on a calculator, a pocket calculator. And these were limited to only one color, and it would display numbers. And if you ever remember seeing an old 1980s clock, like a alarm clock, it would have this kind of style. Actually, it might be 70s, 80s, or even 60s, where they had these kinds of screens. I forget exactly what kind of light. I think it's kind of related to a fluorescent type of light. So it's a bright neon color, and it's boxes. So you're able to display numbers because of the boxes. And the way that a person would give input, these would be hardware buttons. They would punch in whatever numbers they need, and then up here would be functions. So it was a really limited, very limited user interface for interacting with the code. But the software would take the input from this screen, and then it would show the calculation from all that. So if you're interested in exploring a little bit more, these two links give much more information and also simulations for how it works. So it can give you an idea of 1960 till now. That's quite a bit of time. A lot has changed since then. So in contrast to the last screen, here's an example of a simulation software for autonomous vehicles. So this is more like today's world. I got this screenshot maybe in the late 2020, and you could see in this box right here, the most recent release at that time when I got the screenshot was from June 2020. So in that release, you could see that and this is their GitHub page, you can see that they've got a bunch of different languages in order to make this code. So this release, they're open sourced. So, even though their website says here's the news, it's released, the code is hosted at a place that publishes code. What I wanted to show was that a software project from before, I'm just gonna assume it's only like one programming language. Maybe it's two, like assembly plus whatever other language that they used. Or it might be just assembly only. I think one of these sites might give more information to that. So I'm just trying to contrast the fact that there's a lot of different languages here, and different languages means different ways of expressing yourself, different abstractions, and so on. So today's programmer, today's world, I want to say you have to know a lot. You have to understand there's different languages out there, and then some of these languages have to work together. And so for you going off, you're going to be looking for full-time work soon. You're going to have to be able to understand not just that there's different languages, but to be able to go outside of your comfort zone to quickly learn anything else out there. And so that's just the way that the software development industry is evolving. I can definitely say from when I first started programming and like my first job until like recent days, job postings might say like back then maybe 2 or 3 languages, but now we're in the web space. It's not just desktop. I think the simulation software might be desktop based, but if you're working with the web application, cloud services, you may be exposed to job postings that have a lot more languages because they require you to interface with a lot of different devices, a lot of different machines, operating software, and so on. So there's just a lot more happening. So that's kind of why it's so important to understand that there's different languages, and then because of all that, how would you choose the right one, right? So that's kind of like the purpose of this lecture. I think this website, if you go into it somewhere, it's going to allow you to preview the demo. Looking at the contributors statistics from the GitHub page, so you could see there's a lot of different people contributing to this open source project. Because it's a very long time of evolution, there's new problems that people are working on, new hardware to support, and that's another reason why I brought up this autonomous vehicle example, is because cars are also evolving to move from gas fuel into like hybrid into like electric cars. So technology keeps evolving. So here's the link to the video if you want to watch the demo. I won't play it now, but that is a screenshot. And then just one more point is you could see from the screenshot that the graphics there is highly evolved compared to the earlier example from the Apollo guidance, what is it called? Computer. And so if we're talking about creating user interfaces, we've got to think about who's going to be using those interfaces. And oftentimes when we talk about creating software for end users, that means we're creating applications, because we're creating not just system software to make sure the operating system works and works efficiently, but we're creating software for end users to be able to complete whatever jobs that they have. So it could be a word processing application, for instance, right? So being able to create for that is going to be really different from creating a calculator for somebody who's maybe like working in finance and trying to predict which stock will perform better. So there's languages that came about because of the different applications that needed to be built. And here's several applications and modes listed. So we can talk about commercial languages. So COBOL is definitely one that is made for commercial use, for businesses to be able to specify exactly what their database reports should look like. COBOL is one of the languages that allow you to configure a lot of different settings to say, I want things to show up exactly this way. Whereas other languages, when you have data types, for instance, in JavaScript, there's only the number type. There's no integer. There's no like separation between integer, float, and so on. It's all number. Another area could be like a scientific language for numeric stuff. Python's a very popular language these days for machine learning, for data science, and so on. Let's see. Some special purpose languages is made specifically for displaying, presenting information. LaTeX is used for producing very nicely typeset documents, printed documents, so PDFs usually. HTML is for creating markup for rendering web pages nicely. CSS, styles, HTML, and so on. So those are some special purpose languages. And you might hear people argue about like whether these are considered real programming languages. We're not going to dive into that in this class. You'll develop your own opinion of, where would you draw the line of what is considered a language. In conclusion, there are many languages and they're used for different things. Different languages can influence how you approach problems. All right, the next part of the lecture is on the design goals for programming languages. So what should you look for in a language? A good language is a language that fits the problem that you're working on. Okay, so that would be, it leads the programmer to the correct solution of the problem, and then not just getting it done, but also, like satisfactory would be like you can solve the problem. But then to be able to talk about the usability and how easy it is, natural and easy it is to work with a language, that's raising the bar, and like that, is a really good criteria to aim for. A poor choice language will make the problem more complex, add a lot more to your workload. It may demotivate the programmer. And the example that I like to use in some classes, especially 3130, working with the different data structures, because the class is taught Java, I thought a neat way to work with data structures is to just get data out of CSV files, organize the CSV file data, the structured data, into data structures, so it's like in memory for the program, and then try to search for certain values and then write that to a file. So oftentimes I would just say pull a column of data and return it. Now in Java, if you wrote it very nicely in an object-oriented way, in a really proper object-oriented way, you're going to have to define classes, and then you want to define utility functions maybe to work with some of the repeated features that you'd want to work with. But is it necessary? So then if you want to use maybe awk as an example, you can do like a one-liner program that will just say, as you read each row of the whole file, each line of the file, that you would pull out a certain column. And there, I think, is a really good example to show the verbosity of a language, and how one might make the problem much more time consuming to complete. So choosing the right tool for the job can be really useful. So some things to consider when you're picking a programming language include the program design. So you really want to sit down and think about the problem. You want to pseudocode it. You want to think about the inputs. You want to think about the outputs. That would help you identify the data types, how you would represent those, and in how much precision for that. You want to think about any sort of transformations of data. So you want to understand the problem. You want to understand how the program is going to respond to the person using the program that you create. And then you also want to have some level of being able to trust that what you've created is correct. So that's like a verification type of concern to think about. And then finally, the cost. Sometimes you might be limited with your budget, so maybe you want to use open source as an example instead of proprietary software. All right, this slide is about the task that a programmer has when trying to start programming on a project. They have to design the program, right? So they have to select a language as part of designing for that program. So the language should hopefully assist the programmer, should help make the problem that is being worked on a little bit more natural to think about and to express oneself. So you have to think about the abstractions that are possible using the language features. So for instance, the date could be represented as a string or an integer, but if you have date as a number, like for instance, Christmas, December 25th, if you say it's an integer, and then when we talked about types in the last lecture, we were saying that when you have types defined, certain operations become available for that type, because that's what the whole typing system is about. So if you define date as an integer, you can do that, but then would it make sense to have it as an integer type? Because, arithmetic operations doesn't have meaning for dates. So that's one thing to think about. And so ideally, one is carefully considering the language that they are going to pick to solve or to create a program that solves a problem. So you want to understand the problem that you're working on in order to thoughtfully proceed. Another concern is on the readability of that language. What it impacts is the maintainability of your program. If it's easy to read, it becomes easier to maintain. It also can help with your debugging workflow. It could help you reduce errors and so on. Writability is also important to think about. If you can produce a syntactically correct statement in that language, right, you can keep progressing in completing the program that you're working on. If you keep getting stuck, it can get really frustrating, right? So writability matters. And don't try to compare apples to oranges when you're talking about writability, because, for instance, you're not going to use HTML to create a calculator that calculates numbers for you, and maybe you won't use something like assembly to create a graphical user interface. Let's see. Reliability is also important. Reliability means that the program will perform to specifications, and it'll go through the verification process, and then you could have confidence in the program if it all checks out. So general attributes, it's all listed here. Just some of the things we covered, but this just using different vocabulary to express that. And this table is information that I got from the Sebesta textbook, section 1.1. I summarized what was written there into this table to make it slightly easier to understand. So you have 3 main areas of concern. You want readability, writability, and reliability, but it's also separated into all these different characteristics. Right, so then some of these characteristics can help with readability, some can help with writability and reliability, and so on. So what does that mean? So as an example, if reliability matters and we want to be able to verify, then we want to be able to test for type errors. And so that means we want a type checking feature with the language. So that's just an example of how to read what this is written, or how this is summarizing the information from Sebesta section 1.1. You should read that if you want more details. There could be errors in my typing up the paraphrasing of what the author said. Orthogonality is a word that I keep seeing show up in textbooks. It is a little hard to understand that concept. I wanted to bring a little bit more detail to help with understanding that. So this is a concept that talks about being able to write things in different ways. So it's combining it's rewriting your code in different ways, or having different features in the language to express yourself. So Unix is orthogonal, but C and Java are not. So the next slide, if you want to get certain tasks completed, there's a lot of flexibility. So you can, for instance, pipe a bunch of different commands together in different orders. So that's where the mix and match is available. And so that's an example of orthogonality. Next section is on the evaluation criteria. So you might be wondering, so what are the questions that I should ask? What are the checklist items I should be looking for? So the evaluation of a programming language should depend on the application, what is that language used for? So you can't fit a round peg into a square hole. So as an example of, if you want to assess the suitability of assembly to creating a web page, well, that's not the right problem for that language at all. So, don't try to force that. Not a good idea. What I'm going to introduce with this lecture is how it's evaluation criteria. In this paper cited below, there's 4 main categories described. There's language design and implementation criteria, there's human factors, software and engineering criteria, and application domain. So he says, although he can group all the different criteria into 4 different groups, you should definitely look at the project-based criteria. So you want to think about what is being produced. So does the language help solve the problem at hand? That's like the most practical question that one can ask, and that should definitely be asked along with all the other different criteria. And then the other thing that he advises is when developers are about to begin programming, before they begin, they should really think through what are the exact criteria needed. So I think he was writing more towards to people who might be managers alongside developers, so not just solely developers. So he's saying people who are in the programming role should also contribute to conversation. And then he also suggests that these criteria should be written down, and probably in a checklist format. That could possibly be the most useful way as you shop around for different languages and then assess its suitability. And so I summarized what he shared. So he looked at literature written by other researchers, and he summarized ideas from all these different individuals, and also had his own ideas. So this is just a summary. You should definitely be a good academic in terms of having the proper process, which is going to the primary source yourself. Even though it is nice that this person, James Howitt, summarized from different papers that he read, the most proper academic flow is to go to these papers as well, take a look at those, make sure that what is summarized is correct. But also, just to give you a overview, this table is presenting some of the questions that one can ask for each of the criteria categories. The textbook from Sebesta has this table format, so it kind of looks like what I had before. Actually, let me go back to that slide. So that's where I got the structure. It's the columns and rows from Sebesta's table, but with more detail. So then finally, to wrap this up, common or best practices. I just want to use some memes to kind of go at the the different language features. So you can look through these to get a sense of, for instance, if you have Lisp, you would use a lot of parentheses, right? So it just kind of jokingly, humorously shows some of the unique characteristics of different languages. So you just want to keep in mind, you want to know enough to know how to use different languages. All right, that's it for this lecture.